Hello everyone. Welcome to the IEEE SISGST Tech Series. I am Atharva Madare, the Computer Society Head at IEEE SISGST. Today, we are talking about a technology that quietly powers almost everything around you, from your phone unlocking with your face to YouTube knowing exactly what you want to watch next. We are talking about neural networks. Now, don't worry if you have never touched AI or ML before. This session is designed specifically for beginners. No heavy math, no jargon overload, just simple, intuitive explanations, a bit of history on how this all came to be, and by the end, you'll even write a few codes or to see a neural network learn something with your own eyes. So let's get started. Let's start with a simple question. How does your brain recognize a friend's face in a crowd? You don't consciously calculate anything, you just know. That's because your brain has billions of neurons, all connected, all passing tiny signals to each other, and together they recognize patterns instantly. A neural network is a computer's attempt to mimic this idea. Not the biology exactly, but the concept of many small units working together to recognize patterns. In simple terms, a neural network is a system that takes an input, processes it through layers of small mathematical units, and gives an output, like a prediction or a decision. Before neural networks existed, how did computers make decisions or predictions at all? Let's rewind a bit. Before neural networks, programming was mostly rule based. If you wanted a computer to identify spam emails or detect an object in an image, humans had to sit and write explicit rules. Something like if the email contains the word lottery, mark it as spam. This is called rule based or symbolic programming. The problem is that real world patterns are far too complex and varied to capture with handwritten rules. You simply can't write a rule for every possible handwriting style or every face shape. Alongside this, there were early statistical approaches like linear regression and decision trees, which could find patterns in data, but they struggle badly with complex, messy, real world data like images, speech, or language. The concept of neural network actually goes back to 1943, when Warren McClough, a neuroscientist, and Walter Pitts, a logician, proposed a simplified mathematical model of how a biological neuron works. This was purely theoretical. There were no real learning happening yet. The real breakthrough came in 1958 when Frank Rosenblatt, a psychologist, built the perceptron, the first artificial neuron that could actually learn from data by adjusting its own weights. It caused huge excitement and people believed machines would soon think like humans. But in 1969, researchers Marvin Minsky and Seymour Papert proved that a single perceptron couldn't even solve simple problems like XOR logic. It just wasn't powerful enough alone. This caused funding and interest in neural networks to collapse for almost 2 decades, a period that is now famously called the AI winter. Things changed again in 1986 when Geoffrey Hinton and its colleagues popularized the backpropagation algorithm, the very technique we'll actually use in our code demo today, which finally allowed multi-layer networks to learn effectively. This reignited interest in field. For a long time after that, neural networks still couldn't beat traditional methods, mainly due to limited data and limited computing power. That changed in 2012, when a deep neural network called AlexNet dramatically outperformed every other method in a major image recognition competition. Combined with the rise of powerful GPUs and massive datasets, this kicked off the modern deep learning era that we are still in today. The same era that eventually gave us things like ChatGPT and Claude. So neural networks aren't really a new invention. The core idea is over 80 years old. What changed recently is that we finally have enough data and enough computing power to make them actually work well. Let's zoom into the smallest unit, a single artificial neuron. Think of a neuron like a small decision maker. It takes some input, which are just numbers. It multiplies each input by a weight, which represents how important that input is. It adds them all up, along with a small extra value called a bias. Finally, it passes this result through something called an activation function, which decides the final output. Here's a simple real-life analogy. Imagine you are deciding whether to go out and play cricket today. You consider a few inputs. Is it sunny? Are your friends free? Do you have homework pending? Each of these factors has a different importance or weight in your final decision. You combine all of this mentally and you arrive at a final yes or no. That is exactly what a neuron does mathematically. Now, one neuron alone can only make very simple decisions. Real world problems like recognizing handwriting, detecting spam emails, or predicting house prices needs many neurons working together. This is where the idea of layers come in. First, we have the input layer, which receives the raw data such as pixels of an image or numbers from a dataset. Then we have one or more hidden layers where the actual pattern learning happens, and each neuron here picks up a small piece of overall pattern. Finally, we have the output layer, which gives us the final answer, like cat or dog or a specific number. When you stack multiple hidden layers together, this is what people call deep learning. The word deep simply refers to having many layers stacked one after another. How does a neural network actually learn? This is the most important part, so let's keep it simple. When a neural network is first created, its weights are just random numbers, so its very first few predictions are basically guesses and usually wrong. Here's how the learning loop works. First, there's a forward pass, where the network takes an input and makes a prediction. Next, we compare this prediction with the actual correct answer and calculate how wrong the prediction was. This wrongness is called the loss or the error. Then comes backpropagation, where the network looks back and figure out exactly which weights contributed to that error. Finally, the network slightly updates those weights to reduce the error in the next round. The entire loop repeats thousands of times and slowly the network's guesses becomes more and more accurate. Where do we see neural networks in real life? Before we move to coding, let's quickly connect all of this to things you already use every single day. Face unlock on your phone uses it. Instagram and YouTube recommending content you like uses it. Google Translates uses it. Chatbots like ChatGPT or Claude use it. Voice assistants like Siri and Alexa use it too. All of this, at their core, rely on neural networks that have been trained on huge amounts of data. Let's quickly summarize what we have learned so far. A neural network is inspired by how the human brain works. The idea itself is over 80 years old, starting from a theoretical model in 1943 through the invention of the perceptron, a long quiet period called the AI winter, and finally the modern deep learning boom starting around 2012. The smallest unit of neural network is a neuron. It takes inputs, applies weights, and adds a bias, and passes everything through an activation function. Neurons are organized into input, hidden, and output layers. And learning happens through a repeated cycle of forward pass, calculating errors, and back propagation, adjusting weights over many iterations until the predictions become accurate. Now, let's actually see this in action with a hands-on demo. Don't worry, we are keeping this extremely beginner friendly. Let's start by importing NumPy. NumPy is just a library that lets Python handle numbers and math operations, especially with lists of numbers, very efficiently. Think of it as Python's calculator toolkit. We'll use it to store our data and do all the math our neuron needs. And here are the correct answers for each of those four examples. Our goal is to make the neurons predict these values by itself, just by looking at the inputs above. Now, we set something called a random seed. This just means that every time we run this code, we get the same random numbers, so our results stay consistent and repeatable for this demo. This next line creates our neurons weights. Remember, weights are just numbers that decide how important each input is. Right now, our neuron knows nothing, so we start with completely random weights. Now, let's define something called an activation function. In simple words, this function takes any number and squashes it into a value between 0 and 1. So we can treat it like a probability or a decision. This particular one is called the sigmoid function. We also need the derivative of this function. Don't worry about the math behind this. Just know that this helps our neuron figure out how much to adjust its weight during learning. This is the most important part, our training loop. We are going to repeat this process 10,000 times. Each time, the neuron will make a prediction, check how wrong it was, and then slightly adjust its weight to do better next time. This is exactly how the neuron learns from its mistakes, step by step. Now, let's see what our neuron has actually learned. First, let's print out its final weights after 10,000 rounds of training. And finally, the moment of truth. Let's print the neurons' final predictions and compare them to the correct answers we defined earlier. If everything worked, this number should be very close to 0, 1, 1 and 0, which is exactly the pattern we wanted to learn. And it learned this completely on its own, without us telling it the rule directly. That's neural networks explained in the simplest way possible, starting from their history, moving to a single neuron, then to layers, understanding how learning actually happens, and finally seeing it work with real code. If you want to explore this further, try changing the input patterns in the code and see how the network adapts to them. Also, look up libraries like TensorFlow and PyTorch, which lets you build much larger and more powerful networks with just a few lines of code. Thank you so much for watching this session. Drop your questions in the comments and we'll see you again next Sunday with a brand new topic. Happy learning.